There is a opening and there is a light on one side. Image of the opening is forming on the other side. Now, I want to measure or I want to make a drawing of this opening. Here is the source of light, and I want to see how large is the opening here. Now, I have two things available with me. One is ray optics and other is wave optics. Here, if I take the help of ray optics, it is a point source of light and the one ray goes this way and here is the shadow of this. Then here is the shadow of this, and this is the bright light I get, which is the image of this opening. Okay, which optics I have taken? Ray optics, because these are two rays. Now, I want to see the opening, make a diagram, find out the size by taking help of wave optics. So I say from here, wave fronts are moving. Wave fronts. This. And from here, the waves I know. I will have to make central maxima, then first dark one side, first dark on the other side. In between, I will get the central maxima, and that will be the image of this opening. Where is this? So, I will make it here. Sorry, I will write it again. This is the wave front. When this wave front is here and this distance I keep here, how much will be the opening? The answer is opening is equal to 2 lambda upon A. This is the angle, and with this angle we have to multiply D, and that gives the width, this width, 2 lambda D by A. Okay, this is the width of central maxima. I calculate it here. The D is, capital D is small. Then again I calculate here. Again I calculate here. Again I calculate here. And I see there is a graph for D, and that graph is like this way. And here it is. Here is the dark, 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 and this goes like this way. This goes on going down, 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 and it comes here. This goes up from here. This is the straight line, Whether it is ray optics, whether it is wave optics, the opening will be larger. दोनों में से कोई भी ऑप्टिक्स होगा, ये रे ऑप्टिक्स का रास्ता है. अगर मैंने यहाँ पर स्क्रीन को रखा तो मैं क्या देखता हूँ कि मुझे यहाँ से लेके यहाँ तक लाइट मिलती है. ये इतनी बड़ी लाइट मिलती है, और यही लाइट मेरी ड्राइंग के अनुसार किस ऑप्टिक्स के कारण होती है? तो आंसर है रे ऑप्टिक्स के कारण. अगर यहाँ पर मैं स्क्रीन रखूँगा तो मैं ऑब्जर्व करता हूँ लैब में कि मुझे यहाँ से लेके यहाँ तक ओपनिंग दिखती है इसकी. ऐसे ओपनिंग मैंने पेपर रख के देखा तो मुझे ये जो ओपनिंग दिखती है, ये जब मैं ड्रॉ करता हूँ तो ये रिजल्ट किसके अनुसार मिलता है? इसके अनुसार. एंड व्हाट इज दिस? रे ऑप्टिक्स. ठीक है. अगर मैं इस पेपर को बहुत दूर रख गया, उधर से लाइट आ रही है, ये पेपर को मैंने यहाँ रखा, इस पेपर को मैंने यहाँ रखा, तो अब मैं क्या देखता हूँ कि मुझे लाइट यहाँ से लेके यहाँ तक मिलती. लेकिन अगर मैं रे ऑप्टिक्स की ड्राइंग बनाता हूँ तो रे ऑप्टिक्स के अनुसार मुझे यहाँ से यहाँ तक मिलनी चाहिए. ये किसके अनुसार है? रे ऑप्टिक्स के अनुसार. ये किसके अनुसार है? वेव ऑप्टिक्स के अनुसार. मुझे मिलती क्या है? कौन सी ओपनिंग मिलती है? आंसर है जो ज्यादा होती, which is larger one. So here I get an opening, this one. इतनी लाइट मुझे दिखती है, और ये लाइट को मैं कैसे एक्सप्लेन करता हूँ? वेव ऑप्टिक्स से. वेव ऑप्टिक्स से मैं एक्सप्लेन करता हूँ कि फर्स्ट डार्क नीचे, फर्स्ट डार्क ऊपर, दिस इज द ओपनिंग, एंड दैट इज व्हाई वी गेट सो मच width of the central minima. यहाँ पर इतना नहीं मिलता, इतना लाइट मिलता है. I can explain that with wave optics. लेकिन जब मैं उसी स्क्रीन को यहाँ रखता हूँ तो मुझे कहाँ मिलती है लाइट? आंसर है यहाँ से लेके यहाँ तक लाइट मिलती. अगर मैं वेव ऑप्टिक्स से एक्सप्लेन करूँगा तो मुझे इतनी मिलनी चाहिए, लेकिन एक्चुअल कितनी मिल रही है? इतनी. और ये मैं एक्सप्लेन किससे करता हूँ? रे ऑप्टिक्स से. ऐसा पेपर रखा, बोला देखिए जी ये 5 थी, ये 6 है, 5 थी, ये 6 है. 6 क्यों मिली? मैंने ड्राइंग बना दी. ये देखिए ये 5 है, ये 6 है, और 6 कहाँ है? यहाँ से लेके यहाँ तक. अगर मैं वेव ऑप्टिक्स की ड्राइंग बनाऊंगा तो वेव ऑप्टिक्स में ये 5.5 आएगा. 5 से तो बड़ा आएगा, पर 5.5 आएगा. लेकिन मुझे लैब में एक्चुअल कितना दिख रहा है? 6. I can't explain 6 with wave optics, but I can explain with ray optics. तो मैंने ray optics बनाया, ये देखिए. ठीक है. अब हम इतना दूर चले गए, फिर से उन्होंने बोला किस में आएगी? मैंने देखा जितने में आई है, that is by ray optics. Ray optics is applicable. यहाँ देखा वेव ऑप्टिक्स, यहाँ देखा ये बड़ी ओपनिंग, रे ऑप्टिक्स. यहाँ देखा बड़ी ओपनिंग ये है, द लार्जर वन इज विजिबल एंड दिस इज वेव ऑप्टिक्स. सो यू कैन अंडरस्टैंड मैं कहाँ जा रहा हूँ. इफ आई ब्रिंग माई स्क्रीन हियर 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 एट दिस पॉइंट, कौन सी ऑप्टिक्स लगाना है? यस. फिर से आई स्टार्ट माई स्क्रीन हियर. यहाँ पर इसकी इमेज देखने के लिए कौन सी ऑप्टिक्स अप्लाई करनी पड़ेगी? रे ऑप्टिक्स. हियर रे ऑप्टिक्स, whichever is the larger one, no? Because we will see the complete light. यहाँ हम देखते हैं रे ऑप्टिक्स, यहाँ देखते हैं रे ऑप्टिक्स, यहाँ देखते हैं वेव ऑप्टिक्स. वेव ऑप्टिक्स, वेव ऑप्टिक्स, रे ऑप्टिक्स खत्म. कहाँ खत्म हो गई? यहाँ पर खत्म हो गई. दिस इज लिमिट ऑफ ray optics. So I should change the words. This is limit of ray optics. So whenever we see image of an opening up to certain distance, we have to measure the distance according to ray optics. After that, these images will be formed according to the rules of wave optics. So this particular distance is a very important distance, and this is known as Fresnel's distance. Fresnel distance for this image, and we give it a symbol Z. Now, how much is this distance? On which quantities it depends. So Fresnel distance Z depends on wavelength and aperture, that is opening. Okay, how can we make it? The answer is, so we have to make certain definition of Fresnel distance. We have made a definition, and see the definition. If I draw a line from this center point to this center point, this, at this distance we can prove that this distance, this one, is equal to this total A. This is how much A. So this is A, this is A. And how much is the total? 2A. This is how much A. This. At this point, they are comparable to each other. And here, we have two equations. One is, what is the angle made at this distance? Answer, it is A, and it is radius Z. So A upon Z is the angle made. A upon Z. But we know the deviation for this wave. Deviation for wave is given by a relation, and this is what? For this wave optics, this is the position of dark, and this is the position of first dark. First dark here, first dark here. And what is the angle for first dark? Lambda upon A. So angle for first dark is lambda upon A, and the same angle we have taken by arc upon radius, that is A upon Fresnel distance Z. So A upon Z is delta theta, here delta theta, and lambda upon A is also delta theta. This is in wave optics, this is in ray optics. So this gives us Z is equal to A square upon lambda. This is Fresnel's distance, Z Fresnel. So remember, Fresnel's distance Z is equal to A square upon lambda. And what is this useful for? For all our calculations of images and other calculations, we will work with ray optics up to a certain distance. And what is that distance? That is Fresnel's distance. Suppose I ask you, we have a wavelength which is equal to 500 nanometer. Okay. 500 nanometer. This is wavelength. The opening we have taken as 1 millimeter. A. That is 1 into 10 to the power minus 3 meter. Then, if we are working with a light which has got wavelength this much. Okay, this is yellow light, approximate. This is aperture of our eyes. Okay, 1 millimeter. Then, what is the Fresnel distance for us? Answer, Z is equal to square of the A. So this is 10 to the power minus 6 divided by lambda, 500 into 10 to the power minus 9. This is equal to 10 to the power 3, 10 to the power 3 divided by 500. This comes to 2 meter. That means for my eyes, if I measure the things up to 2 meter, then I should make all my drawings with ray optics methods. Yes, so that is why in our lab, whenever we want to find out an image on my copy, on my board, all these things are within 2, 3, 4 meters. So I take help of ray optics. I don't make wave optics for making small images. I don't make central maxima. I don't consider central maxima for making small images because I keep on working within Fresnel distance. So this is how, when we find Fresnel distance, we can, within that, we can work with simple geometry of ray optics. So this is Fresnel distance. If the distances are very large compared to opening. So if we are decreasing the value of A, then Z will also decrease. Suppose we are doing Young's experiment where we want wave optic effect to be more than ray optics. What do? We decrease the value of A. When A is decreased, then what becomes prominent? What becomes prominent is wave effect. And we are able to see the fringes. That is why A has to be very small. Okay, so this is Fresnel's distance, which is a limiting case of ray optics. Thank you. We have studied Doppler effect in class 11th in the topic of sound. What does it say? There is one source of vibration and there is one observer of the vibration. And this is generating out the waves with certain frequency nu. He is listening with nu naught. If there is no relative motion between the two, then nu naught is same as nu. There is no relative motion between the two, they are moving with the same speed. But if speed of one is more and this is less, the distance is increasing, then the apparent frequency of this is different. Again, if the distance between source and the observer is changing, whether they are coming close or they are moving away, in both the cases, the apparent frequency, what is observed by the observer, become different. This is Doppler's effect. When there is relative motion between source and observer, the frequency as apparent to observer is different and there is a change. According to relation this, where nu, original frequency, delta nu, change in frequency, V, relative velocity. So, if the relative velocity is positive, the frequency decrease. Velocity positive, frequency decrease. That is given by minus. If relative velocity is negative, then frequency increase. If this is negative, then minus into minus plus, delta nu is positive. So, this is relation. And what is C? Velocity of light. A small condition in this is that velocity should be very much less than the velocity of light. Then this is applicable. Another thing, it is slightly different from Doppler's effect in sound. In sound, the Doppler effect is symmetric. Sound, Doppler's effect, asymmetric. That means when the observer moves, there will be change in frequency, delta nu 1. When observer is not moving, but source is moving with the same velocity, there will be again change, delta mu 2. But this change and this change are different. So from this side, if the source is moving with certain velocity v, the frequency will change. But if this does not move and this moves along with this with the same velocity, there will be a change in frequency. But both these changes are different. That is why this effect is asymmetric. This we have studied in class 11. But in light, whether observer is moving or whether source is moving, in both the cases, the change in frequency is same. So we say Doppler's effect is symmetric. So either of the two, source or observer, any one of them moves, the effect is same. In sound, effect is different. This is asymmetric and symmetric. Now one thing here, which we are discussing, if the two objects are coming closer to each other, how is the change in frequency? The relative velocity is negative and the change in frequency is positive. The frequency will increase. Now, if the frequency of light increase, what happens to its color? The answer is the color will be changing, and with increased frequency, the color will slide towards blue. If the frequency decrease, the color, what appears to us, will slide towards red. Red has got lowest frequency and blue has got highest frequency. Now, if I am here, there is a star which is moving away from me. What will be the change in frequency? Will the frequency decrease or increase? Answer, the velocity is positive. Positive. So, change will be negative. So, the frequency will decrease. If the frequency will decrease, then spectrum of the light from that star, if that was stationary and now it is changing frequency, that light, that spectrum will change the color, and that change of color will be towards which side? Red side or blue side? So answer is red side, because frequency is decreasing. Here is our frequency, and the highest frequency is violet, blue, and here it is red. There is a star which, if not moving, has a light corresponding to this frequency. But if I find the star is moving, then if the star is moving, I find that the light which is coming is showing me a spectrum here. What happened to frequency? This frequency has become less. If this frequency has become less, why? Answer, frequency become less when something has positive velocity moving away from me. So when a star is moving away from me, then its light moves towards red. Its spectrum shift towards red. So this I call red shift. Okay, now one line question. What is red shift? Answer, red shift is shifting of spectrum from a star towards red end of the spectrum. Towards red end of the spectrum due to decrease in frequency. This is known as red shift, which indicates that star is moving away. And if that star is coming towards me, then its natural light will show a frequency which is higher than this. So I will see its spectrum here. This. And this will be known as blue shift. So, lights of star may show red shift, reddish part more, bluish part more. If it is shifting towards red, then it means it is moving away. If the light coming from the star compared to my spectrum in the lab, if it is towards bluish side, then I say the star is coming towards me. This is known as red shift, blue shift, and this is an offshoot of Doppler's effect. So you have to remember a few things about the Doppler effect. Number one, its formula. What is Doppler effect? How much is Doppler effect? Property of the Doppler effect. And what is meant by red shift and blue shift. So this is all about Doppler effect in light, and there may be certain more things which you will study in advanced classes. Thank you.